Start the recording already. So for today, we will start the discussion on the internal force. So until yesterday, all of our discussion is about the external force. So we have never discussed about the internal effect on a structure. Okay, so for today, right, we will start the discussion on the internal effect due to all the external loads on a structure. So what is the internal effect and what is the external effect? As you can see in the figure, if you have things like that, up until now, whenever we have a things, right, we only discuss about the external force like shown here as a F1, F2, and F3. Okay, but the effect is actually the effect which is happening on a structure. Actually, it's not just those external forces and the gravitational forces. Okay, not just external forces and gravitational force, but when we take a look inside of the structure, as normally we have an internal effect. Okay, internal effect is a force or moment which is happening inside of the structure. What I mean by inside is really inside of the structure. So if we imaginary cut structure, okay, we will find out that at the cutting area, okay, there will be internal effect in the shape of internal force and internal moment. Okay, so in bahasa we call it as a gaya dalam. Okay, in bahasa we call it as gaya dalam. Those internal force. Okay, or moment dalam. Those internal moment. So when we talk about internal effect, we have two types, which is the first one is internal force and internal moment. So for example, okay, if we have a structure like this, simply supported structure like this, okay, up until yesterday, what we discussed was just what is happening to the structure if we have an external force like this, or yesterday we learned about the distributed force as well, right? So we learned that if we have a external force and distributed external force as well, what is the response of the structure? The response here, the response that we are talking here, was just the external load response. Okay, and plus one more thing, which is the gravitational force. Okay, the response that we are talking about is the response which is happening at the supports. So if we draw the a free body diagram, this is what we will have. And here there is an external reaction. This one as well. Something like this. Okay, this is what we learned up until today. So when we have an external force on or external distributed force or gravitational force, what will be happening and what is the response at the supports, something like that. Okay. So when the things that we learned up until today was just this one. Okay, external effect only. And the things that we will learn starting from today is internal effect. Okay, external effect means that all the external loads plus the gravitational force. Internal effect, on the other hand, is what is really happening inside this particular beam, for example, or inside the two force member, or inside the multi-force member, something like that. So that's the thing that we will start. The things that we will start studying from today. So we will study about the internal effect. Okay, the internal effect that we are talking about, we will have two types. The first one is the internal moment, internal force. The second one will be internal moment. Okay, internal force and internal moment. And normally the internal force, we can divide it into two as well. This is the axial force, internal axial force. And the second one will be the shear force. Okay, so that's the thing that we will study starting from today. Up until this point, any of you want to ask question? No one here want to ask question? Not yet.
I'm sorry, sir. That's the internal force is shear, and what's that about? I cannot read it.
We will have a shear force and axial force.
Axial.
Yeah, axial.
Oh, okay.
I'm so sorry that my writing is so bad. So it's hard for
okay,
you to read.
Sir, mine is worse.
Okay, so that's the thing that we will study starting from today. And what is actually internal effect? What is actually the internal force and the internal moment? So basically, when we learn about structure up until today, what we studied was just finding the response which is happening at the support, or the response which is happening at the other member, the response which is happening at the particular member due to the other member. That's the thing that we study up until today. But when we talk about internal effect, we will talk about what is really happening. Okay, what is really happening at this particular cut, which means at this internal point here or here or here, what stress which is happening there internally. Okay, sorry, not stress. What is the internal force and the internal moment which is happening there internally? So that's the thing that we will study today. So that's what we call as internal effect. And I believe, because yesterday I told you guys to do so, you have watched the second video that I post in the MS Team, for all the classes. Okay, so basically there, the second video talked about the internal force, which is happening at a certain point in a structure like that. Okay, in a member like that. Okay, I think I will continue because I'm sorry that the slide is still in Bahasa. So basically, this one is internal effect. Okay, the internal effect that we may have, right? The internal. So this one we call this as internal effect. Okay, internal force, internal moment, something like that. So the internal effect, we can divide the internal effect into several types. Okay, based on the direction. Okay, based on the direction and the whether it is a force or moment. So the first one is we normally call this as axial force. Okay, in the things that you will study up until you will study next, we normally call this as axial force. Then this one is shear force. Then, so the internal axial force, internal shear force, then internal bending moment, and the last one is internal torsion. So those four are things that may come up when we talk about internal effect. So when we talk about internal axial force, this is what we normally discuss. Okay, when the direction of the load, right? When the direction of the load is like that. Okay, it's in the direction of the member like that. When we talk about the shear force, it's perpendicular to the direction of the member. So instead of going, if the member is like this, instead of going outside or inside, it's going perpendicular to it. This is what we call as shear force. This one is going to the same direction as the member. We call it as axial force. Then bending moment is something like this. Internal bending moment, right? The one that we talked about. And the last one is torsion, like this. The difference between torsion and bending, right? The difference between torsion and moment bending. Okay, the moment bending will create a moment like this, but torsion, okay, torsion, it will twist. It will twist the things that is it will twist the things that is applied on, something like that. Okay, so those four we will talk about quite a lot in the internal effect, especially these two. Although it's not necessarily we will omit these two as well. So basically, when we talk about internal effect, there will be four. Okay, shear force, internal shear force, internal bending moment, okay, internal axial force, and the last one is internal torsion. Okay, so I think before we go here, I will add another things, right? So maybe some of you, I believe some of you still quite confused about what is the meaning, what is the meaning behind internal force or internal moment. Okay, so basically like I will give you one simple, okay, one simple example on this particular problem. Okay, so please imagine you have a structure like this. Simply supported. Here we have a roller here, and here we have a pin. Okay, and the structure is under a very simple load, which is happening is exactly in the middle. For example, here we have 10 kilonewton, and the length here 10 meters. Okay. If I ask you to find out the external effect, okay, this is the things that we normally study up until now. Yeah, this is the things that we normally study up until now to find out the external effect. So we first draw the free body diagram, right? And exactly in the middle here, we have 10 kilonewton. And here we have AY, here we have BY and BX. Okay, this is what we call as the external effect, finding the external effect. Okay, then using sigma fx equal to 0, we will find out that px is equal to 0. Using sigma moment at a equal to 0, then we found out that Py multiplied by 10 minus 10 kilonewton multiplied by 5 equal to 0. That's why we will find out that Py is equal as 5 kilonewton. Using sigma Fy equal to 0, then we will find out that Ay plus Py is equal to 10 kilonewton. Because Py is 5 kilonewton, then Ay is equal to 5 kilonewton. So this is the external force. Sorry, this is the external effect that we normally try to find out. External effect. Internal effect is completely different. But most of the time, in order to find the internal effect, we have to find out all the external effects first. Okay, so we have to find out all the external effects first. Then after that, we can go for the internal effects. So the internal effect, this is one of the example. I want to find out what is really happening at 2.5 meters from the left edge. I want to find out what is really happening inside of the structure, okay, at 2.5 meters from the left edge, like this. So at this particular point, internal effect at this particular point. I want to find out there what is really happening there. Okay, so basically what we're supposed to do is to find out at that particular cut what is really happening there. Okay, what is the internal force which is really happening there, and what is the internal moment, which is really happening there. How can we do that? The easiest way is to cut exactly at the point where we want to find the internal effects, like this. So this is the easiest way to cut it here. We make a cut there. Okay, we make a cut. So after we make a cut there, what we're supposed to do? So basically, after we make the cut, we can divide the structure based on whether it is part of the left side of the cut or the right side of the cut. Okay, you can imagine if we have things like this, then we cut exactly at this particular point. Okay, we cut exactly there. We cut the structure there using this particular line. Okay, in order to make it easier, okay, I will use different color. Okay, the blue line there represents the cutting that we do. Okay, after we do the cut, then we can analyze the left side of the cut and the right side of the cut. Okay, if we take a look at the left side of the cut, I will ask one of you guys. Marsha. Hello, Marsha.
Yes, sir.
Okay, Marsha. Now, I want to take a look at the left side of the cut, Marsha.
Okay.
Yeah. If I see if I want to see the left side of the cut, then if I draw the free body diagram of the left side of the cut, it's most likely like this, right? So this one actually represent the part where the cutting happened.
Yes, sir.
Okay. So now, what is the internal? What is the external effect which we're supposed to include it there? The left side of the cut, based on this particular free body diagram. What do you think?
The force to the right.
The force on the right?
To the right, sir.
Yeah, the force to the right. We have the force to the right. I'm just talking about the external force that we have there, that we're supposed to include in this particular free body diagram.
Oh, the AY.
AY, correct. Yes, AY. So basically we have AY here on the left edge, right? Okay, and this one is the left side of the cut. When we talk about the right side, okay, I supposed to draw the cutting like this. Okay, and for the right side of the cut, what external force that I supposed to include there? External force.
The 10 kilonewton.
Correct, 10 kilonewton.
Bx and By.
10 kilonewton. Then By.
Bx and By.
Yeah, Bx. Okay, so these are the external forces that we're supposed to include in both cuts, right? The left side, the cut, and the left side and the right side. Okay, but when we cut it, okay, when we cut this like this, Okay. If we want to take a look at the equilibrium of the left side of the cut, okay, the equilibrium, I'm telling you, all of you guys, okay, the equilibrium is supposed to be still there. The left cut is supposed to still follow the equilibrium. The same thing happened for the right side of the cut. It's supposed to still follow the equilibrium. Okay, it's supposed to still follow the equilibrium. That's why, okay, I will remove this first because I will do it later. That's why, like it or not, there will be, okay, there will be internal effect at the cutting area, around the cutting area. There will be internal effect there. There will be external force, there will be internal force and internal moment, which is happening there in order, okay, in order to ensure that both the left side of the cut and the right side of the cut still in the equilibrium. Do you get it, Marsha?
Yes, sir.
Okay. Now, Marsha, still for you. If I want to make sure that the left side of the cut equilibrium is still happening on the left side of the cut, okay, what internal force that I supposed to add at the cutted area here? What do you think, Marsha? In order for the equilibrium in order for the equilibrium to be happen at the left side of the cut. So basically, when we cut, the equilibrium will still be there at both sides of the cut area, both sides of the cut parts like that. What do you think, Mas?
The force to the right, sir.
The force to the right? No, I mean, in order for the equilibrium still to happen there, okay, the left side of the cut supposed to follow these two equations, right? Sigma fx equal to 0, sigma fy equal to 0, and sigma moment equal to 0, right? That's what
Yes,
we
sir.
talk about equilibrium, right? Left side of the cut. So we have to create, we have to ensure that these two equations still true for this particular free body diagram. In order to do so, then we have to ensure that we put the correct internal effect there. Do you get it? But what I mean, Marsha? So the
Yes,
internal
sir.
effect, yeah, the internal effect supposed to be there in order to ensure that the equilibrium is hold true like that, Marsha. So what do you think that? What internal effect that we supposed to be, which that supposed to be there at the cut, at the cutting at this particular area, at the cut part? Hello, Marsha.
Sir,
So just to make sure, so the internal effect in the cut section is basically the one to replace the forces, being cut off to maintain the equilibrium.
Yes, correct. Yes, correct. So
So it's
basically,
kind of like
take a
a
look,
replacement, gitu.
not necessarily replacement, but actually, the meaning is what you said is part half correct. So when we talk about the left side of the cut, okay, the 10 kilonewton will not be there. Py Px will not be there because it is not part of the cut side, right? And but like it or not, these three equations will still have to be have to hold true. We have to still hold true this three equilibrium equation because the equilibrium is still there. That's why, like it or not, at the cap area, there must be an internal effect to make sure that this three equation is still there. Now the question is, what kind of internal effect that is supposed to be there in order to ensure that the equilibrium is still hold true?
Oh, I see.
You get it, right? So for
Yeah.
example, the easiest one, sigma Fy equal to 0. Okay, it is still maintained in this particular free body diagram. So in that case, like it or not, we have to add internal force at the cut area here. Okay, vertical internal force, right? Correct or not?
Correct.
And the direction is supposed to be going down or going up. I said
Going down.
Going down. It's supposed to be going down. And the value is supposed to be what? I said, in order to make sure that sigma Fy is equal to 0.
Equivalent with
This one, right? Equivalent to
5
this.
kilonewtons.
Yeah. So it's supposed to be 5 kilonewton. Then by adding this, I ensure that sigma Fy equal to 0 is still hold true, right?
Right.
Okay, now sigma Fx equal to 0. Do we need to add anything there in order to make sure that that one is hold true?
Not necessarily, sir, because it's already 0 from the start.
Yep, because it's already 0. Now the last one, sigma moment equal to 0. If we have a 5 kilonewton on the left and 5 kilonewton on the right like that, will the sigma moment equal to 0 is automatically fulfilled? What do you think, Azad?
But sir, do we have to refer to a point for the sigma moment?
Yeah, it's up to you. You can refer to any point that you want there in the free body diagram.
But it already holds for 3, sir, because it's the forces are already symmetric.
Yeah, the forces is not symmetric. Okay, it's anti-symmetric because the left side is going up 5 kilonewton, the right side is going down 5 kilonewton. And if I try to check the sigma moment, for example, on the left side, there will be 5 kilonewton multiplied by 2.5, right? So there will be moment there. The sigma moment equals to 0 is not automatically fulfilled. Okay, so like it or not, in order to ensure that sigma moment equal to 0 is still hold true or fulfilled, okay, the current moment, which is happening due to the 5 kilonewton going up and down, right, is actually clockwise. So we have to add counterclockwise moment. And the value is supposed to be 5 kilonewton multiplied by 2.5 meters. Okay, so in this case, it's supposed to be 12.5 kilonewton meter. If I add moment like that at the right cut, okay, at this particular cut, right, then all of the equilibrium equation is fulfilled. That's why now I can say that for this particular cut, okay, if we take a look from the left side of the cut, we have two internal effects there. We have two internal effects there. Okay, the first internal effect is shear force going down 5 kilonewton. The second internal effect is moment, counterclockwise moment, 12.5 kilonewton meter. Those two are the internal effect which is happening, okay, which is happening at the cut. Okay. Do you guys have any question about this? Any question? Yes, Lalu.
Sir, I'm not understand why the moment is counterclockwise.
The moment is counterclockwise because the moment which is caused by the 5 kilonewton force going up and 5 kilonewton going down actually causing a couple clockwise couple, right?
Yes,
the
sir.
clockwise couple, the value of the clockwise couple is actually 5 multiplied by 2.5, right? Which is 12.5 kilonewton meters clockwise. Okay. In order to ensure that the structure is under equilibrium on the left side of the cut, okay, I have to give internal moment in the opposite direction.
Oh, okay, sir. Okay, sir. So
Okay.
for just for the equilibrium,
Just for the equilibrium. Yep, correct. Because the equilibrium is supposed to be it's supposed to be fulfilled there. That's why the internal moment there is supposed to be counterclockwise. Okay.
Okay, sir.
Sir, just want to
Hmm?
clarify, sir. So to get the internal effect is to draw the force opposite way, sir.
Actually, it's not to draw the force opposite way, but just to calculate using this equilibrium equation, Marsha.
Oh,
So as long as we ensure that these three equilibrium equation still fulfilled, then the internal force that we calculated from these three equation is supposed to be correct. So basically, when we talk about this, right, just now, I found out that the shear stress is 5 kilonewton by using sigma Fy equal to 0, right? I found out that there is no axial internal force is due to this one, sigma Fx equal to 0, using sigma Fx equal to 0. Then the last one, I found out that the internal moment is 12.5 kilonewton meters counterclockwise using this particular equation, sigma moment equal to 0. So basically, after you do the coupling, okay, to find out the internal effect at that particular cut, right? The first thing that you're supposed to do is to implement the equilibrium equation to find out the the internal effect which is happening at those cuts, that cut, like that. Do you get it, Marsha? Okay. Now I will tell you one important thing about this cut. Okay. Just now, we try to take a look from the left side of the cut. Now, let's us do the same thing, but using the right side of the cut. Okay, if I draw the right side of the card, so this is the free body diagram of the right side of the card. Like what just now we have 10 kilonewton here. Okay, then we have here we have Py equal to 5 kilonewton. Px is equal to 0, so I will not throw it there. Okay. So this is our free body diagram, but this free body diagram is not yet complete because we are not yet completed it with the internal effect. Okay, now this is what I normally do. I will assume it first. Okay, I will assume it first. I will assume that I have I will assume that I have internal effect of shear force phi there and internal effect in the shape of axial force of n there and internal effect in the shape of moment like this m. I assume that we have those three, m, n, and phi. Okay. Then I will try to calculate the value of each of those. How to calculate it? Using another equation of this. Sigma fx2 equal to 0. Sigma fy2 equal to 0. And sigma moment 2 equal to 0. Why 2 there? Because the first equation, we already use it here on the left side of the card because it's completely different equation. Okay. I think I'll point out another guy here. Raihana. Hello, Raihana.
Hello, sir.
Can you help me to find out those three internal effects, Raihana? First, try to find out the N, the axial force, using sigma fx2 equal to 0.
Okay.
For this particular free body diagram, if I want to use sigma fx2 equal to 0, what we have there? What are the forces which is going horizontally there?
Only n.
N, correct. Yes, only N, right? So here, N only, then N must be equal to 0, correct, right?
Yes.
So we have it. We have the value of the N. We have the value of the axial force there. So N is equal to 0. The axial force is equal to 0 because using sigma fx2 equal to 0, N is equal to 0. Okay, now the second one. Using sigma fy2 equal to 0, what you will have there?
10 kilonewton and 5 kilonewton.
Yeah, so just put it in the shape of equation.
5 minus 10.
5 minus 10.
Equal
And what
to
else
0.
there?
That's it.
No.
Oh,
You
there's
have to,
n.
no, not n. Here, phi.
Oh, that's v. Oh, okay.
Yeah.
Plus v.
Plus or minus?
Plus.
Plus phi equal to 0. So what you have there? What's the result there?
V equal to 5.
Phi equal to 5 kilonewton. Okay, correct. Then the last one, using sigma moment equal to 0.
It's clockwise.
Yeah, it's up to you. Which point that you want to apply the sigma moment? The left edge or the right edge?
The left edge.
Left edge, yes, that's the easiest one. So sigma moment at the left edge equal to 0. So what will you have there in the equation? This the
Distance is
the distance is 2.5 meters. Here is 5 meters.
10 times 2.5.
10 times
2.5.
2.5. What else?
Minus 5 times 7.5.
Okay, what else?
Done?
Nope.
Oh no.
There is a moment there.
The M.
Okay, m there is supposed to be plus or minus?
Plus.
Plus
M
m equal to 0. So m is equal to?
Wait. Stop. 12.5 positive.
12.5 positive. So this one is 25. Okay, 5 multiplied by 7.5. Oh, positive, yeah, correct. 12.5 positive. So it's supposed to be 12.5 kilonewton meter.
Yes.
Okay.
Okay.
So that's all the internal effect, right? Or anything else? Rehana?
I don't think so.
Yeah. So this is all the things that we have there.
Yeah.
Okay. So this is all the things that we have there. So if I redraw it again, then the final free body diagram, okay, it's supposed to be like this. 10 kilonewton, 5 kilonewton, and because of the internal effect, we will have shear force 5 kilonewton going up here, and we have as well moment 12.5 kilonewton meter. There. Okay, correct, right, Rehana?
Yes, but
Now, I want
Sir,
all of you. Yeah.
wait, sir. So, is the moment on the right side supposed to be like the same moment as the on the
Left
left
side?
side? Like, where are there like the direction is different? Yeah, like this. Like we are picking the positive
thing,
when
yeah.
we go clockwise.
Yeah, that's the thing. That's the thing that I want to discuss after this session. So, don't worry about it. That's the thing that I want to discuss right now. Okay, so all of you, please take a look at this. The second free body diagram, the right side of the cut. Okay, free body diagram of the right side of the cut, and this one as well. This is the first free body diagram, the left side of the cut. Okay, please compare both of it, especially at the cut part. So from the first free body diagram, the left side of the cut, we have 12.5 and we have 5 kilonewton. 5 kilonewton going down and 12.5 kilonewton meters counterclockwise. But on the second free body diagram, we have 12.5 kilonewton meters clockwise and 5 kilonewton going up. Okay. Is there something weird there? Is there something unusual there?
So sir, they must be equal and opposite reactions.
Who said that just now?
Irfan, sir.
Okay, Irfan. Thank you, Irfan. How about you, Asep? Same thing, right?
The
Yes.
positive direction of the moment.
The positive direction of the moon. What do you mean by the positive direction of the moon?
On the left side, it's counterclockwise, but in the right side, it's clockwise.
Yeah. Actually, positive, negative. Yes, we're supposed to follow the rules, but for internal effect, the rules, the rules is slightly different. We have to follow the sign convention, the other sign convention that I will discuss up after this. But the first thing that you notice here is based on the right side of the card, we have 12.5 kilonewton meters back clockwise. Based on the left side of the card, we have 12.5 kilonewton meter counterclockwise, right? 5 kilonewton going up on the right side of the card, 5 kilonewton going down on the left side of the card. Okay. There is one reason why the internal effects is on the opposite direction on the left side of the card and the right side of the card. So basically, I will need another slide here. Okay, basically, if I have to redraw again, right? 5, 5, 12 counterclockwise. So this is the left side of the card. And this is the right side of the card. Okay. So basically it's like this. This is the things that we have read. Okay. Why this and this are in the opposite direction? So there is one reason behind that. When you join this together with this one, join it together again at the cut area, you join it together again. The results that you're supposed to get will be exactly the same as the results that you're supposed to get will be exactly the same, okay, as the previous one without the cut. Okay, if you join it together, 5 kilonewton here will cancel out with this one, 5 kilonewton. 12 kilonewton meters here will cancel out with this one, 12.5 kilonewton meters. So if you join it together, because this and this will cancel out, and this will cancel out, okay, what you will get after you join it together will be like this. 5 kilonewton water going up, 10 kilonewton, 5 kilonewton going up, 10 kilonewton going down, 5 kilonewton going up. That's the thing. So basically, that is why the results must be in the opposite direction, because when you join it together, it's supposed to cancel out. When you join it together at the cut area, it's supposed to be cancel out at the cut area. So there is no more force or moment which is happening there at the cut area, because we join it together. And because the moment and the force supposed to cancel out. So this is what will be happening there at the cut area. You will have whichever side that you calculate, the results will be the same, but at the opposite direction. Do you guys understand about this? Anyone here want to ask question?
So sir, when the both sides are being digabung jadi satu, the convention for the clockwise or counterclockwise positive is becomes
don't think
only one.
about don't think about the sign convention yet, because later I will talk about the sign convention of the internal force, internal moment, the internal effects. But the basic things is all the internal effects. It will be there. It will come out. It will appear when you cut, and you separate the left side of the cut and right side of the cut. Then the internal effects will appear. But when you join the left side of the cut and the right side of the cut again into one big free body diagram, as usual, the internal effects will be gone because it will cancel out. The internal effect from the left side of the cut and the internal effect of the right side of the cut will cancel out. That's the thing. Okay, I said about the sign convention, we will talk about it after this. Okay.
Oh, okay.
About the basic concepts, anyone want to ask question? Darian Patrick,
Yes, sir.
do you understand about this, Darian?
I'm still trying to like process everything, sir. But for now, I don't have any question yet.
Okay. Rizky, do you understand about this? Hello, Rizky. Rizky is not here. Okay. Fasa, do you understand about this, Fasa? Fasa Diara? Hello, Fasa?
Sir, I have a question, sir.
Yes, Samuel.
So if they ask about the internal force at that point, what do we answer, sir? Like,
This answer, right?
so we just say like 5 kilonewtons of shear force, like that, sir?
Yep. About the positive and negatives, I will talk about it after this.
Okay, sir.
Sir,
Yep. Who's this?
is it possible for 2D problems to have torsion moment?
Torsion, you mean? Yes, it's possible. Okay.
Torsion itu puntir ya, Pak?
Puntir, yes.
Okay.
It's possible as long as in the problem it's given, torsion is given. Yeah, it's possible. Okay, I think I will continue with the next discussion. It's about the sign convention. Okay. So as I told you before, right, when we talk about the internal effect, normally we have to put all the possible internal effects there. So whenever we cut, like for example, we have a structure like this under a certain load like that, for example. Okay, whenever we cut, okay, whenever we cut, so like it or not, whenever we cut, we're supposed to put all the possible internal effects. So all the possible internal effects, you can see it like this, plus the torsion as well, as what Matthew said, okay? All the possible internal effects. So we have to put it like this. We have a N, then we have a phi, then we have a moment, and we have a torsion like this. Okay, so this is the combined thing is that the worst possible case that may appear there, which means that all the things are coming up together: the shear force, axial force, moment, bending moment, and torsion, something like that. Okay, in a three-dimensional case, it's even worse. You can see it like this. There is a 6 possible combination there. Okay, normal force, torsional moment, then bending moment in the C direction, bending moment in the X direction, shear force in the C direction, and shear force in the X direction, something like that. But we will not talk about three-dimensional case. So most of the time we will talk about this. Okay. Sorry. This one sometimes it will be there as well. So this is the worst thing that you may come up with. Okay. But most of the time, yes, we have it like this. But sometimes we have to handle things like this as well. Okay. Then I think in order to make it easier for you guys, but after this, I will give several problem example. Okay. But before that, as I told Azar before, we have to discuss a little bit about the sign convention. Okay. Whenever we cut, okay, the sign convention on the right side and the left side for the normal force is like this. So tension is positive, compression is negative. So whenever we talk about the normal force or axial force, and tension is positive. Okay, then about moment, for moment which will give a smiley face, smiley structure, is the positive moment. So basically, if you see this particular moment, right, it will give a smiley structure. Why? Because the moment is like this, right? In this direction. That is why it will give a smiley structure. So if you imagine that you have a ruler like that, I don't have a ruler in my hand right now. So if I have this structure and I give a moment like this, right, the structure will deform like this. Sorry, the structure will deform like it will deform like how say it? It will deform like this. So it will give a smiley face like that. Okay, it will deform like that. So this is the positive moment direction. On the left side of the cut, it's clockwise. On the right side of the cut, it's counterclockwise. That's the positive moment direction. The positive shear is like this. On the left side of the cut, it's going up, positive. On the right side of the cut, it's going down, positive. So if I try to conclude, if we have a cut like this, okay, the positive direction of the normal force or axial force is like this, going outside. The positive direction for the shear force is like this, going down. And the positive direction for the moment is like this, counterclockwise. It's for this particular cut, but for the opposite cut, okay, if the cut is happening here, okay, the positive direction for the normal force is going to the left, going outside. The positive direction for the shear force is going up. Okay. The positive direction for the moment is like this. Okay, so this is the sign convention for the positive direction. So whenever you have a structure and you want to find out the internal effects, the first thing that you're supposed to do is to draw the free body diagram with this positive direction, shear force, normal force, and moment. So later, if the result is negative, it means that the result is negative, because we draw from the beginning that the positive direction. Okay.
Can we use our own preferences for the sign convention?
No, you can't. So
Okay.
this one is the sign convention that we will use in this particular statics and mechanics of material. So if you use a different sign convention later, it will confuse yourself and the lecturer as well. Your positive may be our negative. Our positive will be your negative like that. Okay, so please follow this particular sign convention. Okay, Matthew?
Okay, sir. Thank you, sir.
Okay. So this is the step-by-step that we're supposed to do. The first one is to find support reaction as usual. Okay, and then do the imaginary section, then draw the free body diagram of the imaginary section. Okay, and then use the equilibrium equation. That's the step-by-step in order to find the internal force. Okay, and that's the thing that I already give example on the simple problem just now. Okay, I think exercise problem. Wait a minute.
Excuse me, sir.
Mm-hmm.
So,
Yes.
For the internal forces, we must follow the rule before for the sign convention, right?
Yes, correct.
So, if we were to put it for the external forces too, do we have to follow that sign convention too, or do we still have to state like before?
For external forces, just use the previous rules. So for the external forces, just use the rules that I told you guys several weeks ago. These rules is just for the internal forces. Okay. For the external forces, we still use the previous one, not this one.
So the one where we have to state whether which one is positive moment and negative moment.
Yes, correct. Yeah. Why for the external forces we can do so, but for the internal forces we cannot do so? Is because, as I told you guys right just now, we found out that the left side of the cut and the right side of the cut, right, is supposed to be in the opposite directions, right? It's supposed to be in the opposite direction. So in order to ensure that you don't confuse yourself with the positive and negative, that's why we have to follow this sign convention. That's why if you take a look at this, the sign convention for the right side of the card and the sign convention, positive sign convention for the left side of the card, okay, it's completely the opposites, right? It's mainly because of that. Mainly because when we take a look at the left side of the card, the results there with the right side of the card results there, okay, the results that you will get will be in the opposite direction. That's why we use this particular sign convention in order to not confuse ourselves. Okay.
Yes, sir. I understand. Thank you, sir.
No problem. Okay, I think we will continue with the discussion. Okay, using a 1 or 2 problem example. Then after that, for your homework, I will give you several problems on the external force. Sorry, for the distributed force and this particular internal effect at one particular point. Okay. Later, I will give you guys several homework on this. But first, we have several problems to solve here. Okay. This is the first problem. This is a combination between distributed external force, okay, distributed external force, and the internal effect. Okay, the one in question here is the internal effect at point C. Internal effect at point C. So we will have to find the internal effect at point C. Okay. Fawaz. Hello, Fawaz. Hello, Fawaz. My Fawaz is not here. Muhammad Rizki. Hello, Muhammad Rizki. Why so many of you that whenever I call, don't respond? Seems like you back to sleep again. Adam Putrayando. Hello, Adam.
Hello, sir.
Okay, Adam. Good day. You can respond to me. Then, please help me to solve for this particular problem, Adam.
Okay.
What's the first thing that we're supposed to do, Adam? Here.
Find the force downwards. The integral of W.
Okay, so find the resultant force of the distributed external force, right?
Yes.
Okay. The location is supposed to be. Where is the location supposed to be?
The 1/3 of
1/3 from the left, right?
Yes.
Okay. So 1/3 from the left side, so most likely around here, right?
Yes.
Okay. This is R. And what is the value of R there?
1,800.
800, 2,000, 1,200.
Or 1,200 times 3
Times 3.
times half. Divided by 2.
Okay.
Yeah.
So you get 1,800.
Yeah.
Newton. Okay, so the resultant force there is 1,800 Newton.
Yes.
Okay, then what's the next thing that we're supposed to do in order to find out this particular internal effect at point C?
Do you draw the free body diagram?
Remember this one? No, not yet. We have, yeah, actually you can draw the free body diagram to find out the supports reaction. Okay.
Yes.
So you have it like this one is 1,800 Newton. This is point C. And at point A, what external forces that we're supposed to have there?
AX, AY, and M.
AY, AX,
And M.
A, like that. Okay. Then we have to find out for the external forces, right?
Yes.
Okay, using sigma Fx equal to 0, what you will get?
AX equals 0.
Okay. Then using sigma Fy equal to 0. So you will get-
AY equals 1,800.
Then next is using sigma moment at A equal to 0. What you have? What you will have there?
1,800.
Multiply by
1.
1. Okay. That's
Yes.
and
Plus M.
equal to 0, right?
Yes.
So MA will be equal to
Negative 1,800.
Newton meter.
Yes.
So negative there means that the moment is supposed to be in the opposite direction, right?
Yes.
Okay. So we have 1,800 Newton going up and 1,800 Newton meters going counterclockwise, right?
Yes.
So MA is supposed to be 1,800 Newton meters counterclockwise, like this. Okay.
Yes.
Now I will redraw it again. So we have counterclockwise 1,800 Newton meter, and then AY going up 1,800 Newton, and then 1,800 Newton at 1 meters going down.
Yes.
Okay, this is one. So C is exactly in the middle.
Yes.
This is C. Okay, so the next thing that we're supposed to do is to find out the internal force at C. Internal effects at C. So
Yes.
how to do so?
Do we draw the broken pieces of the left and right side?
Okay, so we do the imaginary cut, right?
Yes.
So we do the imaginary cut, and then we draw the free body diagram, right?
Yes.
So we draw the free body diagram. So basically, actually, this is slightly wrong. Actually, this particular free body diagram. Remember yesterday when I told you, okay, Adam,
Yes.
when I told you, representing the external force as the distributed external force as a concentrated force will only work to find out the external effect, right?
Okay.
Now, remember, right? I told you so. Right?
Okay. Yes.
Yeah. Also, you don't remember.
I think.
So, in order to find out for the internal effect, okay, in order to find out for the internal effect, we cannot draw it as the concentrated force. So we have to draw it as the distributed force.
I see.
So you still have to draw it like this. 1,200 Newton per meter. Something like that.
So do you separate them first and then find the
Correct.
resultant forces? I see.
Yeah.
Okay.
So now we want to do this one, right? This particular cut, right?
Yes.
Okay. You want to do the left side of the cut or the right side of the cut?
Left side.
Left side. You sure about left side? There are a lot of
Uh,
forces there.
Right
The
side.
the right side of the cut is only the triangle internal force, you know. The triangle
see.
distributed force. So that's the thing. Whenever you want to solve about something, try to solve the easiest one.
Okay.
Okay, so for this one, the right side of the cut, so this one, the right side of the cut, this one, is supposed to be easier than the left side of the cut,
Mhm.
right? That's why it's better for us to use this one, the right side of the cut. Now I will try to draw the right side of the cut. Okay, so this is the right side of the cut, right? But
Yes.
now, what is the value of the W at this particular age? It's not 1,200 Newton per meter anymore, right? Now it's
Mm,
exactly in the middle.
Yes.
What is the value there?
Is it 600?
Correct, 600
Okay.
Newton per meter. Okay, now please help me as well to draw the positive internal effects based on our previous sign convention at point C here.
Let's see. So
Draw all of those. What you have? Positive direction of the
and
normal. Yep, normal is going left or right. Positive.
uh, 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 uh,
Always tension. Remember, tension is always positive.
so right.
No, left or this one.
Oh.
Right?
So it was the one circled.
Hmm?
I thought it was the one being circled.
The one
is it-
is no, this one. Yeah.
Oh, okay.
This one, right?
Okay, yeah.
So to the left. And how about feet? The shear force.
Is it up?
How in order to make it easier for you, right? The N is always tension.
Mhm,
The phi is always giving a clockwise moment,
mhm.
and the moment is always giving a smiley structure.
Okay. So
So phi is going up or down?
is it up?
Up. This one. How about moment?
Um, mm,
Counterclockwise or clockwise?
Counter.
Take a look at this. You just need to copy that, right?
Oh, clockwise.
Clockwise.
I see.
So always remember that when we talk about the this side of the cut, right? This is the
Mhm.
positive direction. When we talk about this side of the cut, this is the positive direction. Okay. So
Yeah.
now we have the N, V, M positive direction. Now, the next thing is to find out the value of N, V, and M, right?
Mhm.
Okay. The first thing that I want to calculate is sigma fx equal to 0. What you will have there.
N equals 0.
N equal 0. Then the next one, sigma fy equal to 0. What you will have there.
V minus
V minus
600 times
1.5 meter. This is the line.
600 times 1.5 divided by 2.
Equal to 0, right?
Yes.
Okay, so phi is equal to
$300, 900.
Nah, 900 is just multiplying by 1.5. 900 divided by 2.
450.
550 Newton. That's it. Okay. If I want to represent it with concentrated force here, okay, concentrated force for the 600 Newton per meter. Sorry, for the W for the distributed force. It's supposed to be around here, right? 1.5, 5 meters, 0.5 meters from the left, right? And the value there is supposed to be 450 Newton, right?
Yes.
That's why the phi here is supposed to be 450 going up, because the resultant force there for the distributed force is 450 going down. So, so it's supposed to be correct. Okay. Now, using sigma moment equal to 0, what you will have there? Sigma moment on the left edge equal to 0. What you will have there?
M minus 450 times 0.5.
450 Newtons times 0.5
equals 0.
Equal to 0. So M is equal to
220. Wait.
Yeah, correct.
Yeah. 225
Newton meter. So this is the results that you're supposed to get. Okay. Do you understand now, Adam?
Yes, I understand.
Okay. So after you cut, okay, this is for all of you guys, right? After you cut, if the cut there is already fixed at certain location, for example, X or 1.5 meters, then there you can represent the distributed force with resultant force like this. Okay, but if for example it's like this, if it's like this, right, like the main free body diagram, this is sometimes the mistakes that students do. Okay, this particular free body diagram, just now we do the free body diagram like this in order to solve for MA, AX, and AY, right? Then sometimes students make a mistake like this. Okay, now AX, AY, MA is already found. Then I want to find out for the resultant force, for the internal effect which is happening at point C. Then students draw it like this. Then students draw it like this. Okay, seems like this one is easier because there is nothing there. Okay, so later, some of the students draw it like this. Okay, so this is my free body diagram. P going up and going to the left. And going to the left, moment is like this. But nothing is here. Okay, this one is the wrong free body diagram. Because remember, whenever you talk about the internal effect, okay, whenever you talk about internal effect, you cannot directly represent the distributed force with one conservative force, because it will not be valid all the time. This is one of the cases where it's not valid. Because in reality, there is a load there. Okay, from this to this, there is a load there, distributed load, distributed force there. So it's supposed to be there. So the load is supposed to be there. It's not necessarily just by representing it here, it will be represented in this particular cut. No. So you have to draw the distributed force there. Like this. This is the correct one. Okay, do you guys understand about this?
Pak,
Yes, Matthew.
for the left cut, if we look at from the left cut, the area of the triangle it will not be a triangle.
Yes, it will not be triangle.
Also, a clockwise movement will not be a positive value for the bending moment.
For the cut, yes, because later when you draw it from the left, right, this is what you will have like that. Okay, so the distributed force will be like this. So later you will have to combine triangle and rectangular. Okay, and we have this one, 1,800 Newton, 1,800 Newton meter. And then at point C, the positive of N will be going to the right, tension, Phi will be going down, okay, and M will be counterclockwise. Okay, here there is a 1,200 Newton per meter. Here is 600 Newton per meter. The value of the W is varying from 1,200 Newton per meter to 600 Newton per meter. And if you do the calculation here, the results must be the same with this one as well. Okay, Matthew?
Okay, Pak. Jadi yang counterclockwise moment here is considered as positive moment, ya, moment bending moment.
This one, yes.
Yeah.
It's considered as the positive there.
Okay, Pak.
So if you find out that the result here is positive, for example, here, this one, using the positive bending moment on the right side of the cut, okay, we found out that the M is positive, 225 Newton meters. And if you use the left side of the cut, by assuming that the positive moment is counterclockwise, the results will still be positive 225 Newton meter. Do you get it, Matthew? So what
yes,
you
sir.
have to do is just to follow the sign convention. By doing so, positive means positive, negative means negative, that's all. Okay. So it already handled the change of the change in the change of the positive direction of the left side and the right side of the cut. So what you have to do is just to see whether the value is positive or negative. When it's positive, it means that the direction is correct. When it's negative, it means that the actual direction is supposed to be the opposite of what you draw. Okay.
Okay, thank you, sir.
For this one, what you have to do is to practice more. This is another problem example that we can try to solve together. So we have something like this, and we have to find out the internal effect at point B, for example. So if we want to draw the free body diagram to solve for the external effect first, there is a distributed force like this. Okay. At point A, there's supposed to be AY, AX. At point C, because this one is supposed to be two force member, DC, CD is supposed to be two force member. That's why we have to draw it FF, SF. This one, the angle is slightly wrong. FCD, like this. So this is the first free body diagram it's supposed to solve. Okay, the centroid is in the middle. So you can replace the distributed force with one resultant force. The resultant force there is supposed to be 50 pound force per feet multiplied by 8. So 400 lbf. That's the representative concentrated force. So we can delete the distributed force and replace it with the concentrated external force. Concentrated force like that. Exactly in the middle, 400 lbf. Okay, then using sigma Fy equal to 0, sigma Fx equal to 0, sigma moment equal to 0, you can find the value of Ax, Ay, and FCD. Then after you find out the value of those three, then you can solve for the section B like that. Okay, the section B, right? Later, this is the free body diagram. If I use the left side of the cut, then we have AY, AX. AY and AX here, you're supposed to replace it with the actual value that we get from the first free body diagram, the first calculation here. Okay, then we have a distributed force. £50 per feet. This one. And then at the right side of the cut, the left side of the cut, we put the positive sign of N, positive sign of free, and positive sign of moment. Then using sigma Fx equal to 0, sigma Fx2 equal to 0, sigma Fy2 equal to 0, and sigma moment 2 equal to 0, then we will be able to find for N, V, and F. That's the way to do it for this particular problem. Okay. Regarding this internal effect, anyone want to ask question here before I conclude the class? Anyone here having a problem with this?
Sir,
Yes, Jovan.
can you move to the previous slide?
Son?
Yes, this one. So here you put the moment at C, right? At the cutting point.
Yes, yes.
Isn't both of the moment clockwise?
Both of the moment clockwise. No. The top one, okay, this one, this particular free body diagram actually showing the right side of the cut, right? The moment is clockwise, yes, there. The moment is clockwise, but for this particular free body diagram, the moment here is counterclockwise.
Wait, no, sir. I mean, for the calculation for the right side, isn't it supposed to be M plus 450 times 0.5?
Which one? M plus 450. Ah, you mean this one? Oh, yeah, correct. Okay. Yes, thank you, Jovan.
Yes.
You are correct. So this one is supposed to be M plus 450 Newton multiplied by 0.5 meters equal to 0.
Yes.
So this one is supposed to be plus. That's why the result is supposed to be minus. You mean that way, right?
Yes.
So,
So
the
then-
actual moment there in here is supposed to be counterclockwise then, 225 Newton meters. So the moment there is supposed to be 225 Newton meter counterclockwise. Yes, but this is for the first free body diagram, okay?
Yes.
Not the second free body diagram. Okay, thank you, Jovan.
So then, sir,
Yes.
does it mean that the moment doesn't apa yang the positive one?
Mana? Maksudnya?
Kan tadi ada yang positif gitu kan? Yang apa kalau momen positif? Jadi kalau ini momennya nggak positif gitu?
Yeah. So basically, this one, the value of the moment is negative, right? So it's supposed to be the opposite of what we draw there. So it's supposed to be, instead of clockwise, it's supposed to be counterclockwise.
So this is a negative value of moment.
So, but actually the easiest way is just put it as negative. The meaning is counterclockwise using the first free body diagram. Okay.
Okay.
Why we supposed to use the negative value? Because if we use the second free body diagram, this free body diagram, right? Okay. The value of the moment will still be negative. This one, negative 225 Newton meters. You get it?
Yeah, I get it.
So if we use the second free body diagram, the direction of the moment there is supposed to be clockwise.
Clockwise, yeah.
Yeah, plus clockwise 225 Newton meters. But in order to prevent the confusion, okay, instead of putting it like this, just put negative there. Negative means the opposites of what you draw.
So we put negative, but we still put it as clockwise direction.
No, just put it negative. So
okay.
Negative means it's the opposite of the drawing like that. Okay.
Okay. Thank you, sir.
But in reality, yes, the moment there is supposed to be 225 Newton meters counterclockwise using the first free body diagram. Do you get it, right?
Yes, I get it.
But in the second free body diagram, in reality, it's supposed to be clockwise.
Yes.
Because it's supposed to be the opposites of the drawing. That's why the easiest way is just put negatives there. Okay?
Okay. Thank you, sir.
Thank you, Jovan, for correcting me. Yeah, I didn't realize that I made a mistake. Okay, I think that's all for today's class. It's already 1 minute past 9 in the morning. So after this, please check the MS Teams, and in the afternoon, I will post your homework for next Thursday. Okay, see you guys next Thursday. Okay, bye.
Thank you, sir.
Yeah.
Thank you, sir.
Thank you. Bye.
Thank you, sir.
Thank you, sir. Thank you, sir.